The lab for this is called rate law fading crystal violet.
On day 1 of the lab, we started by setting up the colorimeter by plugging it into the logger and plugging the logger into the computer. Next, we used distilled water in a cuvette to calibrate the colorimeter by inserting it and seeing the value of absorbance on the computer screen. And then finally, we used a fixed amount of distilled water in crystal violet ranging from 2 to 10 milliliters and created stock solutions ranging from 5 to 25 macromolar.
On day 2 of the procedure, the colorimeter was set up similarly to day 1 and this time was calibrated with sodium hydroxide. Solutions were prepared ranging from 5 to 25 micromolar with varying volumes of sodium hydroxide and crystal violet. The transmittance of each solution over time was recorded, and with this data, the concentration that was most ideal to use was determined.
This data table shows the different concentrations of each sample in macromolar and the different amount of volume of distilled water and crystal violet needed to make them.
This data table shows how the absorbances of solution vary by concentration in macromolar.
This data table shows how absorbance changed over time in the 15 micromolar solution of crystal violet and sodium hydroxide. As time went on, the absorbance went down.
We chose to do the 15 macromolar solution as our value because it gave us the absorbance readings closest to 1.
The calibration curve shows how absorbance always increases with concentration. Our best fit line models this relationship. This graph shows how absorbance changed over time in the 15 micromolar solution, as it always decreased.
The model that best represents this data would be an exponential decay graph.
To calculate concentration, we divided any given absorbance by the calibration curve slope.
For example, we took the absorbance of 0.388 and divided by 0.0367, giving a value of 10.6 concentration. This graph shows the natural log of the crystal violet concentration against the time. Because this graph is roughly linear, it can be assumed that the reaction of the rate is overall first order. This graph shows 1 over the concentration of crystal violet versus the time and how it increased at an exponential rate. Because this model is not linear, it can be assumed that the rate of reaction is not second order overall. As stated earlier, because the log natural graph is linear, this means the rate of reaction overall is first order. The rate constant in this case would be the slope of the line of the log natural, which would be 0.0079. The correct unit to determine this would be seconds to the negative first power. In the reaction, there were 2 chemicals, sodium hydroxide and crystal violet. The 2 of them recorded very quickly after they were mixed. A source of error would be waiting too long after the 2 reactants were mixed to put the cuvette in the colorimeter and measure the absorbance and transmittance. This would make the value of absorbance lower than expected. However, one way to possibly fix this would be to pour the crystal violet and set it in the colorimeter before pouring the sodium hydroxide. After pouring sodium hydroxide with the crystal violet, quickly put the lid on and measure absorbance to stop this from happening. Because the slope of the natural log times the concentration of crystal violet graph was 0.0079, the final rate law would be 0.0079 seconds to the negative first power, our constant, times the crystal violet concentration. And that was it. The rate law of a fading crystal violet.